Hello, welcome back to the Jerusalem Science Contest. This is week 6, the 6th lecture, Detection of Ionizing Radiation, which may be found on page 99 of your textbook. And once we finish this, we'll actually be at the halfway point of our discussions on radioactivity. So today I want to talk about how we actually go about detecting ionizing radiation. We haven't really said anything about that thus far. And in addition to what's in your book, I'd like to show you something which is not there, which is really the precursor of how radioactivity is detected today. And it was the way that Marie and Pierre Curie did this back in the late 1800s when they were doing their pioneering work on isolating radium and polonium from uranium. So they actually had to find a way of being able to detect the radioactivity of the various fractions as they were attempting to purify this material. So they used something called an electroscope. And I've got theirs actually was probably a lot more sophisticated than what I'm using. I know they used the gold leaf electroscope. I actually made one. I don't know if you can be able to see this too well, but I made one out of just a jar, some kind of a food jar that my wife had in the cabinet. And basically what it is there's a wire, there's actually a little copper coil on the top of this, and there's a wire attached to that copper coil, and hanging down from the wire, it's kind of hard to see this. I'm going to see if I can get if I can actually rotate this at an angle where you'd actually be able to see there's two leaves of aluminum. Because of the reflection, I'll have to turn this sideways a little bit, I think, in order for you to be able to see it. But you should be able to see these two aluminum leaves that are hanging down. Now, I can charge this up. I've actually got a comb right now, and I'm combing my hair. And if I actually, as I comb my hair, I'm actually transferring electrons from my hair to the surface of the comb, which is an insulator, and then I'm going to reapply those electrons to the tip of this device. And what should happen is that the two leaves, hopefully you'll be able to see this, yes, will actually fly apart. And they will remain apart for some period of time until cosmic radiation, which we're constantly being bombarded by, is actually going to cause, because what we've done is we've actually taken these two leaves, put negative charges of electrons on both leaves, that causes the leaves to actually open up like this. And then as we're being bombarded by cosmic radiation, there's a number of alpha particles that are going to be produced. There'll be some positive charges that will cause this to dissipate. Well, if you put a radioactive substance into this device, you'd actually get, depending on how radioactive it was, you could actually time how long it would take for those two leaves to collapse. And the greater the radioactivity, the faster they would collapse. And the Curies actually had, in their device, they actually had a little way of actually measuring the angle between the leaves, and they could see at what rate the angle was actually decreasing. So they were able to determine how relative radioactivity of various fractions of radium or polonium. So what we're going to talk about are principally what we have for the more modern types of detectors. We're going to be discussing principally two main types of detectors, and then some other miscellaneous types. So the first types of detectors are what are referred to as gas-filled detectors, and then we're also going to have scintillation detectors, and then finally there's going to be this miscellaneous category. So I want to begin with the gas-filled detectors, and the simplest kind of gas-filled detector is what is known as an ionization chamber. And basically what it is just it's going to be a chamber to which is connected an electrical power supply, and it's going to have an anode and a cathode. And let's see, can we see this? So you're going to have a battery over here. You're going to have some form of power supply. You probably have a number of these things in here. And there'll be an anode and a cathode coming in here. And basically what you're doing then is this would be the cathode over on this side and the anode over here. And so we're going to actually be able to produce electrons in this device. What we're doing is we've got electrons. This portion right here will be electron rich, this will be electron poor. In between here, if we can ionize, get sufficient ionization of the air that's actually in here, so we've got oxygen and nitrogen and whatever other air components happen to be in there, a little bit of argon, we can actually start to ionize these molecules and or atoms that are in there. And what we can find is that we can actually get, once that's ionized, once these atoms become ionized, then the negatively charged ions will move from here, will move from the cathodic side to the anodic side. And this can be set up in such a way that it actually produces some kind of signal. So we can actually get a signal out of this, and this is something that we could actually measure then. The voltages are relatively low. They're between 50 volts, which isn't much, and they go up to as high as about 300 volts for this kind of device. So this is the simplest kind of detector. There's some problems associated with it though, because it turns out with an ionization detector, it's very good for detecting bulk radiation. If there's a lot of radioactivity, it's good for that, but it's not particularly sensitive. So that can cause a problem if you've got very low levels of radioactivity. But where it is used and where it's very much appreciated is in devices that are called dosimeters. People that work in, for instance, in nuclear power plants might wear these devices. Anybody that's going to be working around in areas where they might encounter fairly significant amounts of radioactivity at any given time would be advised to have one of these dosimeters. And basically what it does is it's basically getting all of the counts, all of the disintegrations that are being produced are going to cause some kind of deflection on a meter, and that will actually, it will be cumulative. So you have some kind of a meter in there, and the more radioactivity that you actually see, the greater the deflection will be, and then the meter can be reset at some point in time, but it actually tells you how much radiation you're receiving over a given period of time. So that's important. That's an important thing to know. So these kinds of things do have their place, but they're not, if we're trying to do, and they're also not terribly accurate. Your book says there's about a 20% deviation in accuracy in these devices, so that's fairly significant. As I said, they still have a place in industry. Now there's another kind of counter which uses a higher voltage, and this thing is known as a proportional counter. And the proportional counter has improvements over the ionization counter because you're using a higher voltage. One of the things is, and you're also not going to use, in that kind of a counter, you won't use this air-filled, even though it's gas-filled, it's not filled with air, it's not filled with oxygen, but it is filled with gases like argon. One of the problems with oxygen is that oxygen tends to absorb electrons, so a lot of these things are actually, since these things are actually relying on the movement of electrons, the oxygen in there actually kind of interferes with the process. So if you want to get better detection, get rid of the oxygen and use a higher voltage, and then put argon in here. So you can put argon into this space, and with a higher voltage now, and then we have we can make something called a proportional counter, and this is able to detect a single ionization pretty readily. As I said, it's argon filled, and what's actually happening here is because of the higher voltages, we're actually, in this case, what's actually happening is because of these higher voltages, you tend to get a lot more ionization occurring, because what will happen is the electrons, as they move, actually accelerate towards the anode, so they go faster and faster and faster. And in the process, they will encounter, for instance, argon atoms, and they will hit the argon atoms, and that will trigger the formation of other electrons. And we can actually get if we allow this process to continue, we get something called a cascade or an avalanche. What we actually find is that for one electron that's actually produced, let's say by a beta particle entering the chamber, that electron is actually going to be augmented by the time it gets over to the anode, which is the detector side. We will have gotten as many as 1 million ionizations from that. So we get about a 10 to the 6th potentiation there. We're getting about 10 to the 6 more ionizations in this kind of detector. The reason that it's called a proportional counter is because the total charge that's being produced here is actually proportional to the energy that's deposited by an incoming particle. So that's why it's known as a proportional counter. These things are, as I said before, we can detect individual counts, and that's very, very important when we're dealing with low levels of radioactive material. Now, I don't have either a proportional counter or a dosimeter, an ionization chamber that I can show you, but I do have the next type of device, which is shown on page 101 of your textbook, what is known as the Geiger-Miller tube, also known as the Geiger counter. And I do have a Geiger counter. Geiger counters, I'm not sure when the first Geiger counter was probably made in the early part of the 20th century. But these things became used quite a bit right after the Second World War, particularly like in the Korean War. And I actually, somewhere around here, actually have a Korean War from that period. I actually have a Geiger counter from that period. It's not functional. But I have another Geiger counter. I also have a civil defense Geiger counter that was probably used in the early 1960s. And they keep improving these things. They make them better. And I've got another Geiger counter, which is the one that I tend to use a lot for my demonstrations. And this one was probably made in the early 1980s. But here's the Geiger counter here, and you can see, I'll show it to you. So it's basically got all of its electronics in this little box. The Geiger tube itself is actually attached to this. There's a wire that goes to the box, and here's the Geiger tube, and I've actually taken the shield off of it. So there's usually there's a plastic shield that's placed on it. I put the shield back on to show you. So it's normally shielded like this. And if we turn the Geiger counter on, the way the Geiger counter actually works is, again, it's a similar kind of thing to what we saw before, because we've got, but we're going to use much higher voltages now. We're going to use voltages around 800 volts. Now there's only, I don't know, maybe 15 volts or so actually of batteries inside this this little box here. I don't even think it's that. I don't even remember how many batteries are. There might even be less than 15 volts, but it's certainly no more than that. So there are a number of step-up transformers in here that actually increase the voltage to give us 800 volts once it's turned on. But that's enough to actually activate the Geiger tube. And with the Geiger tube, what's happening is again, this is usually an argon-filled tube. And what's happening is the electrons are going to accelerate to the anode, as they did in the last situation. And they produce, when that happens, they're producing excitation of the argon atoms. Now, the argon atoms can emit X-rays and other kinds of photons, which can cause secondary ionizations to occur. And just like the proportional counter, where we got a potentiation, with a Geiger counter, the potentiation is actually about 10,000 times greater. So we're looking for each ion that enters here, we can actually get about 10 to the 10th, or about 10 billion secondary ionizations to occur from that. So that does also create some problems for us, because very, very rapidly there's a tendency for all the gas inside the chamber to become ionized. So we actually have to put something in there that's called a quenching gas, and it usually is something like a small amount of a halogen, like chlorine, that is actually placed in the chamber because these excess photons that are being produced during these ionization processes. You've got a couple things that are going on here. One is that you've got all these electrons that are accumulating on the anode, and basically at that point everything in here gets ionized. Then you've got the positively charged argon ions then start to migrate towards the anode where all the electrons are, where all the electrons have actually accumulated. And once that actually happens, then, because you actually build on the wire here, you actually build up these kind of a cylinder of charge, and then as these argon atoms begin to migrate, they're much slower moving as they actually, the positively charged argon ions actually migrate over there, then the electrons begin to flow back, or actually accelerate back towards these positively charged cations, and when that happens, more photons are being produced. So that is again starts to cause more ionization. So you need to put this halogen in there, chlorine. Chlorine, in the presence of a photon, you can abbreviate as HNu, actually produces chlorine atoms, individual chlorine atoms, which are written as Cl just with a dot. So that's telling us that it's an atom. So you would get two of those, and then ultimately those atoms recombine to give you chlorine once again. But that actually dissipates the energy of that photon. So that's a way of getting rid of it. Okay. So anyway, let's see. We've got these X-rays that are being produced, and these other forms of ionization that are actually have to be taken care of. Let's see. There's a couple terms that I wanted you to be familiar with. I mean, they're all pretty much have about the same meaning. There are three bold terms on page 102 that really have to do with one of the problems that's associated when you're using something like a Geiger counter, because if you've got too many events actually occurring, what happens is there's not enough time for the detector to actually reset itself. So it takes a finite amount of time for all these charges to be dissipated and for the quenching process to take place. So we have something that's called dead time, which is the time interval between a pulse, that is one of these electromagnetic pulses that's occurring because we have this surge of electrons being produced. The interval after the pulse has occurred, during which the counter is insensitive to further ionizing events. So that's that period of time that it takes before everything can kind of reset itself, and that's referred to as dead time. It's also really not, it's also basically the same as resolving time, which is the minimum time interval by which two pulses can be separated to be detected as two individual pulses. So the point is that if we've got two pulses that are so close together that we can't actually separate them, we can't really count them. So that becomes a problem for us. And then there's the recovery time, which is the amount of time that it really takes to reset everything. It's the time interval that must elapse after a pulse has occurred before another full-size pulse can occur. So all these things have to be taken into consideration. If two, for instance, and your book makes the point that if two particles, whether they're alpha particles or beta particles, happen to enter the Geiger tube at exactly the same time, what we're going to find is that we have what's called a coincident event, which means that since both of these things are coming in at the same time, only one of the counts is actually going to be recorded. Now that doesn't happen all the time, and there is a way, which is there's actually a graph that you can use, and there's one that's actually shown on page 103 of your book, which is called a coincidence correction graph. So what you would expect is if you look at the counts, the actual counts that you have over a given period of time, and if we plotted the true number of counts on the y-axis, and then we plotted the actual observed counts on the x-axis, if it weren't for coincidence, what we would find is both of the numbers would be exactly the same. So we should get a line that comes up here at a kind of a 45-degree angle. So these were the true counts, and on the other axis we had the observed counts. But what we actually find is that as this number starts to go up, when we actually plot this, we'll find that there's a deviation, and it's going to deviate something like this. Goes up like that, and then it's going to suddenly, got that a little bit too steep, it's going to suddenly start to curve off and go like that. And so by looking at the observed counts, we can actually use this kind of a graph to correct and actually find out what the true number of counts are that we're getting in there. Because we're going to look the true counts is going to be higher than the observed counts. That's what that's showing us. Okay. So those are basically gas filled gas filled detectors, and I wanted to just give you a bit of a demonstration. Rabbi Weiner will probably cut this out to shorten the lecture, and you can watch this as a separate thing because this is going to take a little while. But I wanted to show you some things that you can do with a Geiger counter. So first of all, I want to talk about, I'm going to turn this on here for you so you can see what happens. I don't know if you'll be able to see this or not, but first I'm going to remove the cap, and then I'm going to turn the Geiger counter on, and you'll be able to hear a clicking. I can set this on two modes, one that's silent and one that's clicking. And even though I'm not near anything, although I have a number of radioactive things, they're pretty far away, what you're actually hearing once I turn this on is what we would call background radiation. This is basically cosmic rays that we're always being bombarded by. Could even be a few stray particles that are coming from the carbon-14 and the potassium-40 that are in my body. But I'm turning it on, and every time you hear one of these little chirps, that's an ionization. Something's getting into the detector. I'm going to turn this all the way up, or I'm going to turn it down to the greatest sensitivity. So here's the detector. I'm actually holding it up as though we would, in the position where we would expect to see more cosmic radiation. It's actually coming right through the roof of this building, and it's coming down through all the floors of my house. I really can't protect myself from it entirely, but that's what you're hearing. And I'm going to hold this up, see if you can see this. I don't know if you're able to see it or not. So there's a meter on here as well. You notice we just got a whole big flux of cosmic radiation. Every time, I don't know if you can see this or not, but every time there's see if I've got this on the right scale. Oh, I know, that's why I'm not on the right scale. Okay, let's try it now. You should be able to see a deflection in the meter. So now you notice every time you hear a click, you'll notice that the needle actually fluctuates a bit. So that's cosmic radiation. We talked about a number of different radionuclides, and one of the ones that we've talked about quite a bit is something called cesium-137. And I actually have on the side, if you can see this, mounted to the side of this device is a little, and you can see the danger radioactivity symbol on the side of it. It's a little box that's actually used to calibrate the Geiger counter. See, are we able to see that or not? It's a little hard to see. But anyway, it tells us, and there's actually over here is the calibration. This hasn't been calibrated in many, many years, but it actually says on here, if I can read it, let's see, it was calibrated, well, I can't even tell when it was last calibrated. but it has, I believe, 0.1 microcuries of cesium-137. So I'm going to actually open this up, and when I flip it open, you can see inside is this little kind of circular device. That's actually the cesium source. So, and I want you to see what happens when I actually approach the cesium source. So you can hear that we got a lot more clicks, and if you actually were to look at the needle, I'd have to switch the needle to the next lowest position because I actually pinned the needle. It went completely off scale. So I'm going to make it 1/10 as sensitive and do it again. And when I do that, let me see if I can show you the deflection on the needle. See if we can see this. It's still going almost full scale. It's about 2/3 of the way, so you can probably see where the needle is right now. It's about maybe 2/3 or 80% of the way. So what is cesium producing? It's producing beta particles that are getting through. There's also gamma radiation that's being produced. How do we know that? Because I know that this shield over here is fairly thick. It's not thick enough to block out gamma radiation, but it's certainly thick enough to block out beta radiation. So when I put it back with the shield on top, see if you can see the deflection again. Now you'll notice you're still getting deflection, but it's much less. Before it was almost all the way over, and now it's maybe 20% deflection. So that tells us that most of the radioactivity that we're actually experiencing from that is coming from gamma radiation. What other forms of radiation might we encounter in our homes? Well, the one thing that I've already mentioned to you is one of the things that you'll see is you'll see radioactivity in your smoke detector. I have an old smoke detector here. I believe it still works, but I was required by the city that I live in to actually get a new kind of smoke detector. So right over here, where I'm pointing here, this little box, it's kind of a little crypt here. There's some americium-241 in there inside the smoke detector, and it's still fairly well shielded from the alpha radiation, but when I put this up there, you can hear an increase in the amount of clicks that we're getting from the americium. Now, if I take a bare americium source, which I actually happen to have one of, if I can find it, here it is. When I put that near the Geiger counter, it instantly pins the needle. I'm actually going to go to 1/10 of that, and even at 1/10. I'm still going at about 3/4 the scale. So there's an enormous amount of alpha radiation being produced by this. This is I believe is also a 10th microcurie. It might be a little bit more than that. This is a 1 microcurie americium source that I have right here. Excuse me. So it's basically producing mostly alpha radiation. I can hold it in my hand. Because I know that that's going to protect me from the alpha radiation. I would not want to swallow this thing, get it inside my body, because the alpha radiation inside my body would do a fair amount of damage, and that would not be good. But there you can see the little, you actually can see the little radioactivity, and I don't know if you can see, there's a little shiny metallic disc in the center. That's where the americium is. We can actually block the alpha radiation now. And this might surprise you, although it shouldn't, because we already know that alpha radiation is not very penetrating. And we also know something else about alpha radiation. We know that it doesn't move very far through air. So even though when I put this right on top, it's very, very loud, when I move it just about 2 inches away, it's not much more than background radiation. But the other thing I want to show you is if I take a single sheet of paper and place it over if I place it over this and put my Geiger tube on the other side, look how much that signal is attenuated. We're still getting a little bit of gamma radiation, probably, maybe there might be a small amount of beta radiation that's produced by some of the other radioisotopes that are in there. But it's a very, very small fraction of what we got before. It's now I'm now barely moving the needle at all, versus here where I'm moving the needle at least 3/4 scale. So that shows us alpha. That shows us what we can do with alpha radiation as well.